Then let us start the second session of future experiments and future facilities of today. In the morning session, we already had invited talks of upgrades from and updates from ALICE and CMS. And we will, in this session, then continue this with updates from LHCb and Atlas. And our first invited speaker today is Jason Nielsen, and he will give us an update on the physics motivation and detector upgrades for the new era of the Atlas experiment. I will give you a 5-minute warning, Jason, and I'm looking forward to your presentation.
Thanks very much. Indeed, it's a pleasure to be here to tell you about the detector upgrades that are planned for Atlas and also tell you about the physics motivation. My talk today will be about the phase 3, run 3 plans for Atlas and also run 4, although there are several other talks in this meeting that concentrate a little bit more on the run 4 or LHC physics program. So let me start by saying a bit about the terms that I'll use as far as the long shutdowns and the different runs, different physics runs that are at the LHC. When I talk about long shutdown 2, I'm talking about the phase 1 detector upgrade that will be helping us prepare for run 3. Run 3 will be the higher luminosity run at 13.5 or 14 TeV, possible increase of center mass energy. This run 3 will allow us to roughly double the luminosity that's collected by Atlas. And then in long shutdown 3, or what we call the phase 2 detector upgrade, we'll be preparing for the HLLHC. And HLLHC may have run 4 or run 5, depending on how you count things. I will maybe use those two interchangeably. The HLLHC era is marked by extremely high luminosity, and this presents particular challenges for the detectors, as we'll see. The Atlas Run 3 and HLLHC physics program are both very broad programs, as can be expected from this general purpose detector. There are many studies that I won't have time to go into today, so I'll just mention that a lot of them have been covered by various technical design reports, by inputs to the European strategy and snowmass efforts in Europe and the US. These include measurements of Higgs boson production, electroweak measurements, searches for physics beyond the standard model, and even high density QCD measurements. So clearly I won't have time to cover all of these today, but I'll focus on an interesting subset that really motivate the detector upgrades that we are planning for Atlas. Almost all these studies benefit from the HLLHC simulation. Atlas has prepared a detailed GEAMP-based simulation of the upgraded detectors that are used for performance estimates and also application to the physics program. Some of the results that I'll show are extrapolations from current searches or measurements that were done to run 2 in Atlas. I'll start by talking about the muon detector upgrades. The muon detector upgrades are a key component of the phase 1 upgrades preparation for run 3. The Atlas muon detectors have somewhat limited PT resolution, and this kind of limits the L1 trigger threshold that can be used for single muons. The reason is that with the current trigger thresholds, we have too high a trigger rate, and so with this limited PT resolution, even raising the trigger threshold is the only way for us to reduce those trigger rates. Of course, raising this threshold has an impact on electroweak physics measurements. So you see in the plot at lower left, the transverse momentum for leptons coming from a W boson. So by raising that threshold, we actually lose quite a bit of our WH signal, the Higgs associated production signal. The upgrades that are planned for the phase 1 upgrade, and in fact are underway, will give us an improved angle measurement on the muons, especially in the new small wheel region. So in the plot at lower right, you can see the distinction between what we call the small wheel region, which is at relatively small Z, around 7 meters, and the large or big wheel region, which is at 12 meters from the collision point. So this new small wheel is the upgrade that will help us improve the angular resolution measurement for the muons, and therefore help us improve the track measurement. Some more pictures of the muon new small wheel. The muon new small wheel is produced with a detector sandwich of thin gap chambers, small strip thin gap chambers, and micro-megas detectors. So the thin gap chambers provide the fast readout for the trigger, and both the thin gap chambers and the micro-megas give precision tracking. But this fast readout for the trigger is important in the context of improving the L1 response, the level 1 response. The challenge has been that these are very large chambers, large precision tracking chambers. And so the quality control is an important part of production at the distributed sites, the distributed production sites throughout the world. I'm happy to report that commissioning is underway at CERN. So you can see that in the photo at the top right, you can see the new small wheels being installed at CERN. The other important aspect of the phase 1 upgrade is the upgrades to the calorimeter electronics and the calorimeter triggers. So Atlas is making a change in the way that the calorimeter trigger is done. Instead of taking relatively coarse trigger towers that are about 0.1 by 0.1 and delta eta by delta phi, the calorimeter trigger is now using supercells. These supercells are clusters of more finely grained calorimeter objects. And so what this does is it allows the full cell information to be put into the trigger, allows the shower shape variables for the electromagnetic shower to be calculated. And this improves the identification for electrons and photons, even in the level 1 trigger. This improved identification results in a lower jet rate, a better jet rejection rate, which results in a lower threshold. Again, one of the keys for the physics program in Run 3. So this has required some improvements in the back-end electronics, also replacement of some of the trigger boards and the level 1 calo trigger. And you see in the plot at lower right, you see the effect on the level 1 rates. In fact, the level 1 rates with the phase 1 upgrades are even below the Run 2 rates that we have right now on Atlas, that we had for Run 2. So this is an improvement in the trigger rates and should be an improvement for any analyses that use the calorimeter trigger. Now, as far as those analyses, we have some extrapolations of Run 3 measurements and searches that are based in part on Run 2 measurements or Run 1 measurements, and in part on detailed simulations of the phase 1 upgrades. So these particular Higgs boson measurements are in fact based on Run 1 results, which have been improved since then. So we can take these as rather conservative projections. In the plot at lower left, you see the expected sensitivity to the kappa modifiers in the Higgs sector. So these kappa modifiers are scaling of the couplings between the Higgs and the fermions on the vertical axis and between the bosons, the W and Z bosons on the horizontal axis. And I think the takeaway from this plot is the difference between the 300 inverse femtobarn measurement, which represents the end of Run 3, with the 3000 inverse femtobarn measurement, which represents the end of the HLLHC era. You see a similar change in the plot on the lower right, which is the measurement of the couplings or the estimate of the couplings as a function of the fermion masses and the boson masses, the W and Z are in there too. You see the difference between the 300 inverse femtobarn and the 3000 inverse femtobarn projections. And in fact, you can read off what the projections are for 300 inverse femtobarn, showing that for the couplings, we'll have measurements that are on the order of 10 or over 20% for some of the fermions. The searches in Run 3 also benefit from these improved triggers, also from increased luminosity. The channels, the signatures that benefit the most are the ones that have relatively small cross sections. So the increase in luminosity makes a big difference for those searches. As one example, I have the monojet signature, which is recoiling against a WIMP, against missing energy. So this jet plus missing energy signature is usually parametrized by looking at the mass that can be excluded for the mediator, in this case, an axial vector mediator that's in the diagram. And what you see is you see a difference here between the expected limit sensitivity and the expected discovery sensitivity, all for luminosity, integrated luminosity of 300 inverse femtobarns. So even in Run 3, we're able to probe these mediator masses that are on the order of 2 TeV, which is pretty exciting. In other searches, for example, dark photon decays, there's a dedicated estimate of the 300 inverse femtobarn analysis for the Higgs decay to dark photons. These dark photons are not detected directly in our detector, but instead they decay to collimated muon jets. These muon jets are collimated because they're at high PT, and they're displaced because of the dark photon flight path. So the lifetime of the dark photons is non-negligible, and this leads to these displaced muon jets. So you see the results here at the right for the 300 inverse femtobarn analysis, showing that there's a range of couplings for which we have the exclusion with 300 inverse femtobarns. And the last physics signature that I'll show for run 3 is the run 3 vector boson scattering estimates. So there have been several publications or pub notes that have been put out by Atlas on the topic of this vector boson scattering. They include the leptonic signatures for the most part. These leptonic signatures, whether they're WW, WZ, or ZZ scattering, are all accessible at HLLHC, and maybe a little bit less so at run 3. But run 3 gives us a chance to improve upon the results from run 2 and prepare some of the modeling comparisons that we'll need for run 4 and run 5 to HLLHC. Again, as we saw before, the ability to trigger on the lower PT leptons from the W is a key to gaining enough statistics for measuring the scattering. So from the plot at lower left and lower right, you can see the results that might be accessible with the run 3 data set. The plot at lower left really focuses on the run 3 data set and the improvement that we see in the expected sensitivity, or expected significance, as we move from the 140 inverse femtobarns for run 2 to the 300 inverse femtobarns expected with run 3. And the plot on the right, you see a much larger lever arm extrapolation all the way from approximately 300 inverse femtobarns that we expect in run at the end of run 3 to up to 4,000 or even 8,000 inverse femtobarns in a hopeful extrapolation for HLLEC. What you see also on the plot at the lower right is you see the challenge that measuring the longitudinal vector boson scattering poses in particular. Even if the overall or inclusive vector boson production can be observed, the measurement of the longitudinal part specifically is very challenging. Speaking of challenges, the HLLHC physics challenges, that is after the phase 2 upgrade, really are to make the most of the LHC ring. So this will be the culmination of the LHC program, resulting in the ultimate energy, the ultimate integrated luminosity. Simone Pagangrizo will give a talk in Friday's plenary session about the HLLHC physics. I'll say a few things about the physics and a little bit more about the detector upgrades. The key point here is that the very high instantaneous LUMI, the high LUMI of the HLLHC, implies a rather significant pileup. So the number of pileup events is on average about 200 up to 200 per crossing, which results in higher hit occupancies in the detector, extra jets that are formed just from overlapping contributions from pileup events, and additional energy in the calorimeter. All these things tend to degrade the resolution if the detectors are not upgraded. So I'll show you in the next few slides some of the many improvements that are planned to improve the performance. These include, again, following up on the triggering, trying to maintain the triggering performance or even improve it in some cases, a better forward acceptance for leptons and especially for jets, especially for flavor tagging in the forward regions, and a better association of particles to the primary vertex in a couple different ways. This helps in rejecting the effects of pileup by allowing us to focus on particles that come from the hard scatter vertex. So these and many other detector upgrades are planned for long shutdown 2, which will occur before run 4. A quick overview of the upgrades includes the all silicon inner tracker replacement that's shown in the diagram at lower left. The most important part of this inner tracker upgrade is the ability to measure tracks up to a pseudorapidity of 4. And this allows extended B tagging beyond the 8 of 2.5 that Atlas currently has. The calorimeter electronics will continue to be upgraded, allowing us to have a fully digital signal passed to the level 1 at 40 megahertz. The muon electronics will also be upgraded, again, improving the trigger information available to the muon trigger, the L1 muon trigger. And as with run 3, one of the keys is maintaining these trigger thresholds. So in the plot at lower right, you see the effect of these upgrades on the track resolution, so the transverse momentum resolution. And I think it's very interesting to compare here what's observed for the inner detector in run 2 and the combined transverse momentum resolution in run 2, and compare that with the combined resolution that's expected for run 4 after the HL-LHC upgrades. You see that in fact, that resolution will even be improved after the upgrades, despite all the pileup events. The ITK silicon tracker is one of the largest trackers by area of silicon built. It's expected to be approximately 13 square meters of pixels and 165 square meters of strips. One of the key aspects is an innermost layer that is designed to be radiation tolerant up to 1 gigarad, using the so-called 3D pixel sensors, where the collection electrodes extend through the bulk instead of being on the top of the bulk. So these 3D sensors allow us to be very close to the beam line. The pixel size is optimized for flavor tagging and tracking resolution. And there's a lot of work being done in order to make sure that the electronics, the readout electronics for the ITK, are radiation hard at the level that's expected for the innermost region of the LHC. You can see from the plots on the bottom, the extension of the pseudorapidity range from the 2.5 that I mentioned earlier to very good efficiency, even out to the highest values of pseudorapidity out at 4.0. You also see from the plot at lower right, the effect of the upgrades compared to the run 2 results in this operating curve that shows the light jet rejection versus the B jet efficiency. And again, just
5 more minutes.
Thank you, Marcus. We showed on the previous page that in fact, there's an improvement over the run 2 performance. So you could take the black line, for example, and see a significant improvement in light jet rejection in the central region. And even in the very forward region, which is quite challenging, the rejection is not much worse than run 2. I mentioned the trigger upgrades and the data acquisition electronics upgrades. One of the main goals here is to continue to improve the ability to target certain trigger signatures for Atlas. Most of these have to do with leptonic signatures or photonic signatures or tau leptonic signatures. And the key here is having the fine-grained information from the calorimeters. So with this full granularity data flowing from the calorimeters that are shown at upper right, they flow down through the feature extractors, the effects, JFEX, GFEX, and FX that extract the information from these finely grained detector outputs. Then these are passed into the event processors where that information can be used for identification and also for event level combinations. So there are a couple things going on in the trigger that really help with the thresholds. One is this enhanced information about the shower shape of the calorimeter. And the second is the increase in the event filter output, which is an increase over what we have here. This should actually be 10 kilohertz. Sorry about that, instead of 10 megahertz. So this is a factor of 10 increase over what is planned for run 3. One of the new detectors that's planned for the HL-LHC upgrade is the high granularity timing detector. This timing detector has as one of its main goals to associate the jets through timing with the primary vertex. And this is done at pseudorapidities where the tracking efficiency starts to drop off. So this is vertex association for the jets that happen to be, or the tracks that happen to be at high eta. And this is achieved through picosecond level timing resolution. This technology is based on the low gain avalanche detectors, which form a very fast signal in the readout electronics. And you can see in the plot at the lower left that the estimates for the HGTD precision, the timing precision, are expected to be on the order of 25 picoseconds at the beginning of run 4 and no worse than 50 picoseconds by the end of run 4. The steps here are as different parts of the detector start to lose efficiency due to radiation damage. You see in the plot in lower right, the pileup jet rejection as a function of the hard scatter efficiency. This can be tuned up and down by hard scatter efficiency. And you see the pileup rejection reaches factors of 100. It's the combination of ITK tracking and HGTD timing and tracking that contributes to this pileup rejection. Now, as far as the physics, the Higgs coupling measurements will continue to be improved at the HL-LHC. In these plots, you see the results for 3,000 inverse femtobarns, showing that nearly all of these cross-section measurements will be achieved down to the level of better than 10%. The measurements can be reinterpreted in the kappa modifier framework, as I showed before. And you see again here that these coupling modifiers, with a few exceptions, will be measured to better than 5%. Dihiggs production is a very exciting prospect for the HLLHC. The current run-to Atlas limit just released is around 4 times the standard model. And at the HLLHC, this is expected to achieve something close to a 4 sigma or 5 sigma significance when CMS and Atlas are combined. You see in the plots here 2 of the most sensitive channels, the BB tau tau channel, which in the BDT score plot does not show a mass peak, but the BB gamma gamma channel does show a mass peak in the M gamma gamma axis. SUSY searches, especially the ones with small cross sections, will also be greatly improved at the HLLHC. The sensitivity will increase from what we see in the gray region in the plotted left for 80 inverse femtobarns by more than factors of 2 or 3, up to a sensitivity near 1 TeV for the 3,000 inverse femtobarn analysis. And these results are for the neutralino and chargino production, in some cases decaying through the Higgs to BB bar. So these are the cases where not only the leptonic trigger thresholds, but also the full B tagging simulation and the improved performance at high eta are important. So this brings me to my summary. Atlas, as I've told you, projects a broad and deep Run 3 and Run 4 and even Run 5 physics program, full of improved measurements that benefit from improved statistics. So these would be the precision measurements, and also searches with small cross sections will be greatly improved over what we observed in Run 2. The challenging experimental conditions will require new detector upgrades, but I think you've seen that in this talk, some of the performance parameters are even improved beyond what we have in Run 2. So that's very exciting. And of course, all of these results depend on collaboration with the theory community so that we can have the best calculations and the best modeling of our data as we move into Run 3 and Run 4. Thank you very much.
Thank you very much for this update for Atlas. Are there questions? I see applause. Yeah, this was a good good talk. Questions? Maybe, so what I appreciate at the end is that you pointed out that it's of course not the experiment alone. It has to be done jointly with theory. And of course, it's not only the detector and the accelerator, it's also really how you deal with the pileup then in the reconstruction. Would you like to make a few more comments maybe on the software and computing aspects of it, or another aspect which you would like to maybe pick out?
Yes, Marcus, thanks. That's a good point. Let me point out 2 things that are key for these upgrades, but I didn't really have time to go through during the talk. The first is some of the improvements that have been made in the software framework overall. We call it the Athena software framework in Atlas. We've just completed a huge effort to move to Athena MT, which is the multi-threaded version of Athena, which allows us to more fully leverage some of the multi-core systems that we have. And in the future, we're expecting to have a even more parallel Athena-based software for Run 4 and Run 5. So there's been a lot of work to do that, to make the most of the computing that's out there. There's also an effort to leverage more completely some of the high performance computing that's coming online around the world, especially in the national laboratories. And so this could be used in particular for some of the Monte Carlo simulations. So this is really an effort, I would say, on the experimental collaboration side to help port some of these Monte Carlo programs to the supercomputers, to the high performance computing clusters, while at the same time working with the Monte Carlo authors to try to incorporate some of the most efficient ways of merging and matching samples. And I think there's a lot of effort there. I'd point out one thing too, you mentioned the improved theory calculations. If we go back to the Higgs measurements, for example, we see that in fact, some of these are becoming very close or even exceeding our knowledge of the theory cross-sections, our theoretical calculations of the theory cross-sections or not the modifiers, because they're just the standard model couplings, but the cross sections themselves, especially at higher orders, the strongly produced Higgs channels are complicated to calculate. So there's been quite a lot of work in the LHC Higgs cross-section working group to bring together a theory and experiment to achieve the ultimate sensitivity for HLLHC.
Thank you very much. So let's go to the next talk. Diego Martinez Santos will present an update from LHCb.
Okay, do you hear me?
I can hear you.
Okay, I will try to share the slides.
Okay, we see the slides.
Okay, do you still see them?
Yes.
Okay, perfect.
Perfect.
Okay, so yeah, I will tell you about the physics of the LHCb upgrades. So, well, as probably you know, the flavor physics is a powerful tool to access a new physics that's beyond the reach of direct production at accelerators. And that's most notably in searches for new sources of flavor violation or CP violation other than the CKM. Just as an illustration, there is this plot by Gene on the right-hand side, which tells you that, let's say, for order one couplings, which are the new physics scale that you access from the oscillation of the different mesons, and you can see that you can reach, in principle, thousands or even close to 1 million of TeV, but of course that's just an illustration for order one couplings. So LHCb will upgrade to continue improving our knowledge of flavor physics. And we usually speak about two different upgrade phases. The phase one, which will start next year and will run until 2030. That's approved, the TDRs are ready, and well, the detector is there to be taking data next year. All the TDRs, well, the main TDRs are those that I show on the right-hand side. And then there is the phase two upgrade, which should start in 2031. There, well, the expression of interest is published. You can see the reference there on the right-hand side. And well, we expect to have the framework TDR by late this year, like for September. Okay, so after this introduction, this is the outline of my talk. I will first tell you which are the timescale for the two phases of the upgrade. Then I will briefly describe what changes in these two upgrades. And then I will go to the physics content of the talk, where I will describe the sensitivity for several measurements like B2SLL transitions, which are now becoming famous, lepton flavor violation, B-mixing, other CP violation, CP-ionic PDKs, and S2DLL. So, well, the time scale for the two upgrades is shown here in this slide. So the LHCb, the normal LHCb, let's say, finished taking data in 2018. It had a peak luminosity of 4 × 10⁻32, and it accumulated 9 inverse femtobarn. So, well, the upgrade was in principle expected to take data in 2021, but there was this delay due to the coronavirus, so it will start taking data in 2022. That's the run 3 of the LHC. The peak luminosity would be 2 × 10⁻33, the maximum one, which is 5 times higher than the peak luminosity we had so far. Then we have the third long shutdown, and then run 4, where the peak luminosity will be again 2 × 10⁻33. And adding up the two runs, the total luminosity of LHCb is expected to be about 50 inverse femtobarn, which is a bit more than 5 times what we accumulated so far. And then we have the phase 2 upgrade, with the data taking starting in run 5. The luminosity would be 10 times higher than for the phase 1, and well, same for the run 6, and in total we expect 300 inverse femtobarn to be accumulated on tape. So I'm now on slide 7. This is the layout of the phase 1 upgrade detector. Well, the basic layout looks very similar to the current detector, but there are upgrades mostly in the tracking system. So the vertex locator now is made out of pixels instead of what had before these raw phi strips. The trigger tracker is also changed now to the upstream tracker, and the tracking stations have been changed from straw tubes to scintillating fibers. And well, we also dropped the first muon chamber because for the intensities that we had in the upgrade, then it would just be a noisy chamber, let's say. Then, well, the main changes in the tracking were done in order to handle the higher pileup. But on top of that, we also improve our detector resolutions. You can see on the plot on the left-hand side, the impact parameter resolution of the tracks. In black, you have the current detector, or well, the past detector, let's say, and in red, the upgraded detector, and you can see that the resolution of the impact parameter resolution will become better, or is expected to become better. And on the right-hand side, you have the momentum resolution, which also improves a little bit. Something that makes a very significant change in the upgrade is the change on the trigger. Before, we used to have a hardware trigger called the L0, which was a bottleneck for many decay chains. Now the L0 disappears, and all the entire trigger is made of software. And the first stage of the trigger is actually done in GPUs. That's documented in that recent TDR from, that TDR that is there in the top right-hand side. So the GPUs will reduce the trigger rate from the, let's say, 40 megahertz that LHC provides down to 1 or half of a megahertz. And then the CPU farm will process the second stage of the trigger, which will reduce the rate down to a few kilohertz. And then the status of the phase 2 upgrade detector, or let's say the status of the design of the phase 2 upgrade detector is summarized here. There are many components change. In particular, the pixel detector, the vertex locator will also have timing. So instead of 3D hits, it will provide 4D hits to help dealing with the pileup. There will be tracking stations in the side of the magnet to recover low momentum tracks. The tracking stations will have a pixel inner tracker to handle the luminosity at low angles. And then there are also several improvements planned for the particle identification systems, like the reach and the muon chambers. So now I go to the experiment sensitivity. So well, these days we are talking a lot about lepton flavor universality violation in B2SLL. So we observed deviations in the ratios of several of these channels, like B plus going to K plus and 2 muons over B plus going to K plus and 2 electrons. These are observables that are theoretically very clean in the standard model, and what we measured both in the K channel and in the K star channel are small, but that start to be significant suppressions with respect to what they should look like in the standard model. The biggest of them is RK, that we published recently, which deviates from the standard model by 3.1 sigma. But in general, we observe similar trends in similar channels. So this has interpretations in beyond the standard model physics, either by a set prime mediator in the S channel or a leptoquark mediator in the T channel. And well, as we get more precision, the LHCb upgrade is expected to reach 1% precisions in all these ratios, or in most of these ratios. And that could translate into an increase on the significance of the Wilson coefficients of the effective Hamiltonian that are shown in the bottom. So currently we have significances in the order of 4 sigma compared to the standard model. In future, if these anomalies are true, then this can grow down to the 15 or even more than 20 sigmas. A channel that is very related to the previous one is vis-a-vis goes to mu because it's also a B2S mu transition. And in general, they are golden modes for new physics searchers, also because, for instance, in supersymmetry, they are sensitive to new Higgses. We published recently an update of the measurement that is consistent within, let's say, 2 sigma if you make a word average with the standard model. So it's a little bit below the standard model, and that's going in the same direction as all the other dimuon channels of the same type that have the dimuon channels a little bit below the standard model. So this will become more clear in the future, where we expect sensitivities in the order of 3 times 10 to the minus 10 for the phase 1, or even 1.6 times 10 to the minus 10 for the phase 2 upgrade. And also, what we can do with large statistics of BS to mu is to measure the effective lifetime. And there we can reach precisions of 5% with phase 1 or 2% with phase 2. And that has implications for like supersymmetric models, as you can see in the plot on the right-hand side, the delta chi square of supersymmetric model versus the effective lifetime. And that the blue and red bands would be what is allowed or what would be allowed in the phase 1 and phase 2 upgrades. And another B2S mu transitions is the BD2K star mu channel. There we perform a full angular analysis. And again, there are some deviations from standard model, as you can see in this observable called P5 prime, which is one of the parameters that governs the angular distribution. And you can see that in the Q-square region of about 5 GB, there are deviations from the prediction compared to the data. And in future, this will again become more clear as the uncertainties go down. You will get the points in, you would get something like the points in red, or translated to Wilson coefficients, you can get significances as the ones shown in the top right-hand side. And also what is interesting here is that, again, this points to values of the Wilson coefficient in the same direction as the previous anomalies I was showing. But also, it's not only that we will become more precise within this dependency on Q square. You know, as the data set becomes larger, we can also do finer binings, which allows you to test with more precision what's going on. Well, very related with lepton universality violation is lepton flavor violation. That's totally forbidden in the standard model, but it's allowed in models beyond the standard model. So any positive signal here is already a compelling evidence for new physics. And there are, of course, searches for this in LHCb. We got several work results like in B2E mu or BS2E mu. And another lepton flavor violation search that we do is tau going to 3 muons, and there we are competitive with Bell, and the upgrade is expected to be competitive with Bell 2 as well. And yeah, all this will give sensitivities in the order of the 10 to the minus 10 for both B2E mu, BS2E mu, or tau to 3 mu. And well, 10 to the minus 9 for other searches like B2K mu. Okay, so that's related to rare decays. Now we also do a CP violation. One of the main quantities that we measure here is the phase of the vis-a-vis mixing. So the BS mixes to BS bar or oscillates to BS bar with an amplitude and a phase. And in this case, the phase of this amplitude is what we call phi S. And yeah, in the standard model is predicted very precisely, is equal to -2 beta S, and has a precision of 8 times 10 to the minus 4 radians. Now in different new physics models, and in particular in the models for the B anomalies, the new particles can affect this oscillation. In particular for set prime models, they imply that BS has an oscillation at 3 level compared to loop level in the standard model, or for leptoq where you would have a competing diagram at loop level with the standard model. So this has implications for models of the B anomalies, and in particular you can look at that plot there on the bottom right, where you can see in red the values of the set prime couplings preferred by the B anomalies, while in blue and green you get the constraints from the B mixing, and while in particular the green is the constraint from the mixing phase. So we will keep improving on this. Right now the precision is 25 milliradians for LHCb alone, or 19 milliradians for the latest H-fluff combination that you can see on the top right plot. You can see they are LHCb, which is the dominant measurement, but also Atlas and CMS have competitive measurements of phi s, and well, the average gives you a precision of 19 milliradians. But here in the bottom plot, you can see the precision that we will get for phi s on all the channels that we measure it. The dominant one is Jepsi phi, that is they are shown in orange, but there are few others, and all of them contribute to the average. So the combined precision that we expect to get for the phase 2 upgrade is 5 milliradians, which will be like, that's for LHCb alone, would be like 5 times more precise than what we currently have.
You have 5 more minutes.
Okay. Then there are other CP violation measurements. Actually, there are many of them. The mixing phase of the BD, Jepsi K short, where we have competitive results with the B factories, and that the sensitivity that we expect is shown there in the top right plot. There is a similar phase, but not exactly the same one, but conceptually a similar phase in hadronic decays. And that we also expect a very high precision, as you can see in the middle plot, for 2 of the channels, BS255 and BS2K star and IK star. We also measure the CKM angle gamma, where we expect a precision of 1 degree for the phase 1 and a little bit less than half of a degree for phase 2 upgrade. Or well, the CP violation parameters in charm, where you can see in the bottom plots which is the current status now in orange, and which will be the status for the LHCb upgrade phase 2 with 300 inverse femtobarn in purple. And well, another measurement in LHCb that is causing some excitement is the semi-taionic BDKs. These are ratios in which we measure some B hadron going to something with charm, a tau, and a neutrino, and we make the ratio to the same channel with a muon. So both the LHCb and the B factories combined see a 4 sigma deviation with respect to the standard model prediction in these ratios. And what is nice is that can be accommodated again by similar new physics as the one on the B2SLL anomalies. And well, again, we hope that with more precision we can shed more light into this, and the precision for the different ratios is shown in these 2 plots by Franco and collaborators. And you can see that for the phase 2 we can reach precisions at the few % level, depending a little bit on the, if you are more or less pessimistic or optimistic with the ultimate systematic, it can be few % or even below 1%. So well, this is the status of all the main anomalies in flavor physics right now. The first bunch of them is the B2S mu anomalies that I spoke at the beginning. Then we recently have G-2 from Fermilab, and in the bottom, the simultonic anomalies also from LHCb and the B factories. In orange, you have the standard model predictions, and in blue, the experimental values and the deviations in sigma. And you can see, well, there's an interesting picture there. Let's hope it's a real picture. But anyway, with the future LHCb upgrade, all this will become much more precise. Well, all this except G-2, of course. So, well, we will see. And well, we also have S2D mu transitions. These are like the second quarter generation version of the B2S mu ones. These are very interesting in when one searches for resources for flavor violation, because they have the strongest suppression in the standard model. because of the CKM factors. We have worked results in two of them, K short to mu mu and sigma to proton mu mu, where the later result excluded the hyper CP anomaly. We had very low trigger efficiencies in run 1. Also, well, in run 2, they improved significantly, like more than an order of magnitude, but they were still low. For the upgrade, however, we expect a trigger efficiency of 100%, so that will be 100 times bigger than run 1 and 5 times bigger than run 2. So for strange decays, the LHCb upgrade is more than just a luminosity gain, because you benefit really a lot from the fact that the hardware trigger is not there anymore. So here you have the sensitivity projections for two of them, K short to mu mu on the top and K short by 0 mu mu on the bottom. And the expected sensitivity is a function of luminosity. So for K short to mu mu, we will get very close to the standard model. For K short by 0 mu mu, we expect to overtake NA48 with the very first, or let's say the first data of the LHCb upgrade. So I go to my conclusions. So LHCb has a rich program of flavor physics in beauty, charm, strange, and tau decays. Now the question that is coming in the last years is if these anomalies with muons are real, and if they are finally the vaccine for all these exhausting years of standard model-like results. Is that the case? Well, we will provide a very precise picture of this with improved P2S mu transitions, together with interplay with the B-mixing, the lepton flavor violating, and a few other bunch of measurements. Have now a very flexible trigger that will allow us, let's say, to overtake many of the difficulties that we have because of the hardware trigger for hadronic decays, also for electronic decays, and especially as well for strange decays. And finally, the phase 2 upgrade would collect like 30 times bigger data sample than what we have currently right now. And that's all.
Thank you very much, Diego, for the update from LHCb. There, I see one question. Jason, please.
Diego, thanks. I'm very interested in the trigger, which is one of the real big breakthroughs, I think, for LHCb. And I wonder if you can say from the physics point of view, how does this idea of having the free running trigger, or let's say the fully flexible online trigger, change the way that the physics groups interact with the trigger? Does it lock you in more because you need to do the analysis essentially in the trigger, or does it free you up because you're essentially storing the whole data set and can go back and look at it in any way you like? This has not been clear to me.
Yeah, I mean, the thing is, there are several ways to use the trigger in that respect. So depending on the analysis you choose, what do you want to save to tape? Of course, the more you save, the tighter you have to be in your selection cuts, or, because otherwise the bandwidth will explode. So there are analyses which basically just save, let's say, the 4 momenta of the candidates or something like this, very little information. There are others, however, who plan to save as much information from the event as possible, especially if, for things like tuning, flavor tagging algorithms, or using new ideas on the underlying events that help you, let's say, with isolation. So for analysis that in which you expect to change things afterwards or improve, improve the analysis based on information of the underlying events, there we save more information of the events, but for others we just save the minimal amount of information. So it's analysis dependent, let's say. I don't know if that answers your question.
Yeah, I think it does.
Are there more questions for Diego? Maybe a short one, just related to what Jason said with your software trigger. What benefits do you see, for instance, you mentioned in your conclusions, decays, but also, for instance, what is currently a very hot topic, this tetraquark states, molecular states of mesons, or maybe even pentaquark candidates?
Well, that depends on which decay, I mean, into which channel do we search for it. I mean, most of these, well, they used to be called exotic states, but okay, they are, well, anyway, all these tetraquarks, or most of these tetraquarks and pentaquarks are observed in B2J psi decay, so B2J psi plus tetraquark or B2J psi plus pentaquark. Yeah, so for all of this, the trigger improvement is small because you trigger on the J psi, and we were already very good triggering on J psis. However, for any others that are observed in hadronic decays, for those to expect an improvement in the efficiency of, don't know, close to a factor 2 probably, depending a bit on the momentum range of your particles. But for those that we discovered in J psis, the improvement is small because we were already very good triggering harmonious states.
Thank you. So thank you very much for the update from LHCb. We will now hear 2 updates on the upcoming or projections prospects for the upcoming Electron Ion Collider. The first of these presentations will be by Rabah Abdul Khalek, who will talk about a sequential global analysis of proton and nuclear PDFs at the Electron Ion Collider. So we see your slides in full screen, and I will give you a 5-minute warning.
Okay, thank you, Marcus. So as Marcus said, I'll be explaining a bit a study we did together with Emanuele Nocera, who's present here now, and my supervisor, Juan Rofo, and Jim Ether. So this study we've done on the projections of the Electron Ion Collider. As you know, it was accepted last year. Could you please, yeah, perfect, thanks. So okay, disclaimer first, I won't be doing the Electron Ion Collider fairness because, or justice, because I'll be really focusing on mainly DIS, unpolarized DIS, which is mainly the topic of this talk. So apologies in advance. And also, let me move my slide. So the strategy I adopted is introducing first the PDFs I use, and then talk on the projections and the impact of the Electron Ion Collider. So mainly the impact I discuss is on NNPDF 3.1, a proton unpolarized PDF, which is given by this reference here, and the nuclear version NNPDF 2.0, the last version, which is given also in this reference. And then I'll talk about the EIC impact via a study we've done combining sequentially both analyses, proton and nuclear PDFs. And I quote also here the yellow report of the official yellow report of the EIC for more details. Okay, let me start with the proton PDF. So the proton NNPDF 3.1 is basically consistent of parameterizing PDFs with neural networks. The flavors we fit, the flavors that we actually parameterize are basically 7 plus or minus intrinsic charm at initial scale of 1, and if charm is included, we move to 1.65 in GeV. Of course, bottom and top are not considered. And in NNPDF 3.1, we used to parameterize every PDF by an independent neural network, as you can see here. So the architecture is we take input the Bjorken X and the log of the Bjorken X, and then we have 2 hidden layers of 5 and 3 neurons with sigmoid activation function. Then we have at the end, the last neuron is the actual part or parameterization of the PDF. And actually, we parameterize the PDFs in the evolution basis, as you can see here, just because it's faster to solve DGLAP in that basis. And we can mainly disentangle all the light quarks and the gluon. So this is the parameterization. Basically, we have the neural network. We have a prefactor to control the large X behavior, a prefactor to control the small X, and finally we have the sum rules imposed in the parameterization as well, as follows: the sum rules, momentum, and number sum rules. Okay, with this in mind, we can smoothly go to the nuclear version of it, NNN PDF 2.0. And here the parameterization is smaller because we don't disentangle the S and S bar, the anti-strange. The data is not that accurate, and we don't have spatially sensitive data to strange yet. So this is the parameterization we adopt, and of course it's below the charm threshold, so we parameterize it at 1 GeV, the initial scale. As you can see, we adopt a slightly different architecture, slightly different methodology as well. So we, in addition to X, the Bjorken X and logarithm of it, we also parameterize the atomic mass A, of course. So we fit different nucleus, so we need this variable. We have 25 nodes in the hidden layer, and then instead of having independent neural network per flavor, we just have one output layer throwing out all the flavors together. So the common feature is that we control also the large X and the small X behavior, and we have the sum rules. So these are common things. Of course, we get the neutron from the proton via SU2 isospin symmetry, and the same also for the proton case. Okay, now briefly introduced, I'll move to the combined part of the analysis. So whenever we fit nuclear PDFs, this is the figure of merit that we minimize, right? The famous chi-squared. And this is the same figure in both proton and nuclear PDF fits. But then, so of course, we also impose positivity via Lagrange multiplier. So every time we have a prediction that goes negative, we explode in chi-squared, and the fit knows that he needs to make everything positive, and this is a very important constraint in our case. One thing different in the nuclear PDF case is that we impose whenever A is equal to 1 to reproduce the proton case. So this is a very important constraint. So it's also imposed by a Lagrange multiplier. And why is it sequential? Why are we talking about combined fits? Because we exactly use the NNPDF 3.1 as a baseline, as a boundary condition. And as you can see in this plot, I plot the nuclear PDF 2.0 at A equal 1, and I show the baseline that we use, NNPDF 3.1, that doesn't know anything about nuclear sets. And you can see that we, via this constraint, we really recreate or reproduce the proton PDF exactly with all its correlations. So it's a member by member replication. One thing to mention, whenever we use a proton PDF in a nuclear PDF fit, we remove all the nuclear sets from the proton PDF. So like chorus, NuTev, the charge current, DIS data, we remove all this and we move it to the nuclear PDF set. And this is just like a plot to show how much correlated proton and nuclear are. So I plot here in the y-axis is the rho, the coefficient, the correlation coefficient, and in function of x, the Bjorken x. And you can see that whenever so in blue you have the helium, you will expect that, right? So whenever the lightest the nucleus is, the more correlated it is with the proton. And you can see it here. Helium is much more correlated than carbon, than iron, etc. Okay, and this is to emphasize on this interplay between the two. Now we move to the kinematic coverage of both PDFs. So this is before EIC. You can see a large coverage of proton data from DIS, Drelian. You have TT top quark pair production. Z-transverse momentum production data, and you can see the coverage goes to 10 to the minus 4 in X and 10 to the 6 in Q. So there's a large coverage in the proton case. Not so much in the nuclear case. So this is the data we consider in N and NPDF 2.0. It's mainly NC, so neutral current and charge current DIS, and Z and W production from the LHC. And these are the fiducial cuts that we use. So what you need to remember is that it's the lower limit is 10 to the minus 2 with 10 to the minus 4, with 10 to 4 in Q2. Now, when we move to the EIC kinematics, and I mainly consider here the unpolarized DIS. So in the proton case, the EIC will run both. We will have data from both charge current and neutral current DIS. The neutral current are on both proton and deuterium, and the charge current is only on the proton, both from E plus and D minus projectiles. Okay. So the highlighted yellow is the previous DIS data included in the fit, and the new points are highlighted in these markers. So one thing you might notice is that HERA already covers slightly a larger range in low X, and also, I mean, it reaches higher Q2s. But what's interesting is also that EIC has more points in the very large X region. That's only EIC has it here, right? In the nuclear case, of course, as you expect, you have a larger coverage, and this is where really the EIC has a huge impact. This goes down to 10 to the minus 3 and Q of 5, 10 to the 3. And just this schematic plot, this is from the EICL report. It's not schematic, it's accurate actually, but just to say that the uncertainties, so this is uncertainty in percent, it goes proportionally with Q. So you have very low statistical uncertainties at low X, low Q, and it goes slightly upwards when you move in X and Q2 direction. And that's also very important to keep in mind.
You have 5 more minutes.
5 more minutes, okay. So let's boost it. So here I plot the proton PDF impact with and without EIC. It might look a bit disappointing, but I will zoom into it later. You mainly see that the large X region, you have quite some impact here in U and D, and of course U bar and D bar as well. I will zoom out. I'll zoom in a second. What's interesting is that when you remove coarse and UTEV, which is the baseline for the nuclear PDF fit, in yellow you see the proton PDF without coarse and UTEV, and in red you see the same thing but with the EIC. And you can see that if you compare the two, the EIC seems to really provide the information that coarse and UTEV used to provide. That's just to note, this is interesting. So this is a summary of the impact on PDFs, the proton PDFs. You can see at large X in U, there's quite some impact, and this is mainly due to both DIS data CC and NC here. DU to see if there's any symmetry violation in isospin, but well, you can see some reduction at large X. S, we weren't very sensitive to S. I mean, you can see the optimistic is slightly higher here. It's just a fluctuation. And what's interesting to see is that both optimistic and pessimistic has the same impact, which is quite reassuring in a sense. We're not dependent on the scenario used for the EIC scenario of projections. Okay, so now we take this proton PDF and we use it as a baseline in the nuclear PDF, and this is what we get. So you can see larger impact on the nuclear PDF case. So this is helium. This is very light nuclei. So so it has a larger correlation with the proton PDF, and that shows in the large X region reduction, and also from the nuclear data you have reduction in the low X region. This is consistent for all light quarks and light antiquarks, U bar, T bar. S plus has a slightly reduction, the gluon not so much. When you move up in A, so this is copper, you see a larger even reduction, and you see the gold also a larger reduction. I mean, copper maybe slightly more. So these are the main nuclei considered by the EIC actually. And to summarize, you can see here the relative reduction, relative uncertainty, and it's basically translating what I showed before. And yeah, it's more interesting when you look at nuclear PDFs. Of course, there's reduction over all A's basically. We show only here 3, but we've checked, and there is consistent reduction in all A's. Yeah, and mainly it's, I mean, the light quarks, because they're mainly affected by the neutral current DIS, right? Okay, maybe I have a minute. So we studied also an implication of these of the EIC impact, and mainly on the neutrino scattering. So we kind of simulated the cross section that a detector would measure from a flux of neutrino going through Earth by comparing the transmission of the neutrino, if you consider Earth is made of proton versus if you consider Earth more realistically made of nucleus. We take the nucleus to be an average of all the nuclei available. So we take it A equal 31, and you can see that there's quite some difference highlighted by the EIC. You see in green, there's quite some separation between if you consider the Earth made of proton or nuclei. And that's quite nice that the EIC in green, you see, it reduces a lot the uncertainty with respect to the blue that was nuclear PDF without the EIC. So we can really tell the difference now. And very quickly, this is also like another ratio of neutral currents, neutral charge current DIS from neutrino nuclei over neutrino proton. And you can see also this modification, the nuclear effects that got really emphasized when you move to, when you consider the EIC on top of the data. The green is given by the EIC impact. So that's quite an interesting implication we found. Okay, and I'll leave with this conclusion, maybe without resummarizing it. Thank you.
Thank you very much. This was very interesting. Are there questions for Rabah? I don't see yet any hands up, so let me ask you a question. So we just went for the EIC through this Yellow Report initiative, where we more or less said, okay, this is the physics reach which we would like to have. This is what we would like to get out. What does this imply for the interaction region, and what does this imply for the detector? Can you make any comments on that, so that we get this precision out? What is important regarding the measurement capabilities, and or also the type of ion species which we will run at the EIC? Yeah.
What I can say, I'm not the expert on this specific question, but indeed there was a lot of back and forth between the experimentalist and the theorist to find the best configuration of detectors with respect to the most interesting region of impacts we want in based on the observable we want to study. So I can only speak about the unpolarized PDFs, but for example, we had many studies showing different projections of the EIC and different region of interest that the experimentalists basically decided at the end the specific tuning of their detectors according to it. With regard to ions chosen, I think it's the aim was to pick from light to high nuclei, so from helium, copper, gold, passing by iron, I think as well. there's 6 nuclei overall. I don't. I wish I made them explicit, but yeah, they cover like a large range in nuclei. I don't know if I answered your question.
Well, that helped. That provided some extra context. Thank you very much.
Thank you.
We now go to the next presentation. It will be about a related subject. We will now hear an impact of the EIC on collinear PDFs, and Filippo Delcarro will present.
Exactly. Hello.
Hi.
So, I want to thank you first of all because finally I managed to come to DIS with a talk on DIS, and I will continue more or less on the same line of thought of the talk from Rabah, because I will talk on the EIC impact on polarized and unpolarized collinear PDF. This was made, oh, sorry, just for a moment. This was made in collaboration with Chris Kokutsa from Temple and Yiyu Zhu from William and Mary. And in general, I will talk on the first part on the EIC impact on the unpolarized PDFs. And then I will talk on polarized PDF, focusing on 2 different asymmetry, the double longitudinal asymmetry, ALL, and the parity violating DIS asymmetry, APV. So first of all, the motivation of our study, which is more or less what you heard already from Rabah. We have our current knowledge of unpolarized collinear PDF is mostly driven by these following data: inclusive neutral current, charge current, PP bar collision at Tevatron, PP collision at LHC. So we are already covering a really impressive range down to 10 to the -5 and with the Q square up to 10 to the first GeV. But the interesting part of EIC is that it will be complementary to this range, accessing the small and the large X longitudinal hadron structure, and an overlapping kinematic range between ERA and the fixed target experiment, but with a luminosity 3 orders larger, and, as we said already, with a much lower uncertainties and low X. To see, we will explore in this global analysis the unpolarized reduced cross-section, and we try to assess the impact of EIC data on the unpolarized PDF, studying this cross-section in different configuration. This is to highlight different flavor structure dependence, and we will see DIS neutral current, charge current with electron and positron beam. And just as an illustration, I put the structure that we are going to analyze with the sigma R, that we are going to analyze in the neutral current, in the charge current for positron and electron. So you can see we have a different linear combination of different flavor of PDFs, and this allows us to have a much cleaner separation in flavors. This global studies, this global fit was done with the GEM Monte Carlo resampling methodology. We start from a PDF at an input scale, as always, and we use the following fx and x alpha 1 minus x, etc. For the parameterization of PDF at the input scale, we chose a suitable set of parameters initially, and we confirmed them with an initial set of data, starting for the simpler, much easier to analyze, and step by step adding additional data sets and repeating our analysis. So this is a Monte Carlo multi-step procedure where we start from a prior, we confront it, we can compare it with data, extracting the posterior distribution, as you can see in the first scheme here. And then we feed the posterior distribution again in this loop. We resample the data, creating some pseudo data. Again, starting for a prior, comparing with a new set of data, larger this time, and the posterior. So we repeat multiple times this step. And as you can see, for example, in the unpolarized EIC pseudo data, we're starting from fixed target DIS from SLAC NMC. We add the ERA collider data, JLab F2, Drelian, W production, W decay. Now, at Atlas CMS. And finally, in the last step, we included also the sigma-reduced ESC pseudodata. These pseudodata are simply created from the penultimate step and then fit together with all the existing data. So the end game of our analysis is basically comparing the uncertainties of these two last steps and see if ESC actually produce an improvement on our PDF extraction. As you can see, this is the first results for the electron beam on proton and deuterium, not target, but beam again. And we can see there is a comparison of the relative uncertainties for unpolarized PDFs for multiple flavors and multiple combination of flavors before and after the inclusion of ESC data. And you can see that mostly, as we were interested, we can there is evidence of a much better constrained PDF at a low X, mostly in the valence case, as you can see in the U valence, the D bar plus U bar, and also in the gluon sector. So we observe, luckily, much lower uncertainties for the PDF with the inclusion of ESC pseudodata. Here I'm showing the same picture, but it's a little bit outdated, actually, the red curve, the gem curve, because in the previous one we added some new data set and we put a little bit more constraint on the data set, but this is what was published actually in the yellow report. And we compare it with the different results from different collaboration. As you can see, there is a lot of difference actually on different curves by different collaboration, as obviously different groups are using different, are including different data set, using different W square cuts and different methodologies to fit their data. But the message that came out, let's say, the agreed message that came out from this analysis is that the ESC will actually have a huge impact on the PDFs, mostly on the valence case. Here I included also different analysis that we did, including also the positron beam. This positron beam, even if it's not the main focus of the ESC and there's actually a much lower luminosity compared to the electron one, still it's really interesting to observe because it can allow us to access different flavor combination. For example, with in the positron CC process, DAS, with the different charge of the exchange boson, allow us to access unique flavor combination. And in this case, it has the effect of further constraining the type PDFs and the D over U ratio, which can really improve our description of the internal structure of proton and neutrons. Beyond this, the positron beam may also allow access to other effects. For example, the breaking of the strange and strange symmetry, or the parton level charge symmetry violation. This was the results on the unpolarized. Now we move on to the delta G uncertainties, to the polarized case, because even if the unpolarized PDF are fundamental for every study of the internal structure, since the beginning of since the idea of the EIC from the white paper, one of the golden measurement of the nucleon spin structure at the EIC was a precise determination of the holistic gluon distribution function. And hopefully we will maybe solve the proton spins puzzle once and for all. In particular, we will focus on the delta G for the gluon contribution, but also we will analyze the delta F, where F is one of the flavor of our PDF. We will observe two different asymmetries, two different observables, the ALL, where we have a longitudinal polarized electrons of longitudinal polarized hadrons, and the parity violating asymmetry, where again, the parity violating is the most dominant contribution. And we are observing unpolarized lepton of longitudinal polarized hadrons. And through these two observables, we will explore the impact of future ESC data on quark and gluon unicity distribution in the proton, neutron, and the helium-3. So just focusing on the ALL, we see there is, we can describe it through different structure function, focusing mostly on the G1 SQ square. We see a combination of delta Q plus and delta G. Okay. And the important thing that I wanted to highlight here is that we repeated this analysis on proton, deuterium, and helium-3 to see if actually changing this ion beam can improve our flavor description of the polarized and polarized PDF.
Filippo, you have 5 more minutes.
Oh yeah, okay. Here you can see instead the parity evaluating symmetry. Again, we have the description through G1 gamma Z and G5 gamma Z, where we have a different combination. The interesting part is that analyzing ALL and parity evaluating asymmetry, we have an independent linear combination of elicited PDF, which together with G1 allow a cleaner flavor separation. Here I go back again to the GEM methodology that we use. In this case, however, there was 2 different stages. In the first one, we repeated the one similar to the unpolarized one using fixed target data, ARAL, Drellian, and jet production. And at this point, at the end of the first stage, we fix the parameter that entered our description of the asymmetry. We fix the parameter of the spin average PDFs, and we move on to the spin-dependent PDFs. Starting from current data with the polarized DIS from EMC, Compass, LAC, and Hermes, and including also rich jet data and polarized PP. At this point, we created our polarized ESC pseudodata, and we compare these two lab steps. Here we create I'm just giving an overview of the pseudodata that we created for ALL, proton, deuterium, and helium. And here in the lower left for the asymmetry of the parity violating. We create 6 different scenarios with a low, where we variate the central value of our pseudodata by 1 sigma, mid, the central value of our pseudodata, and high, where we go up by 1 sigma. We basically just shifted the central value of our pseudodata. Moreover, we also explore the possibility of imposing or not the SC3 flavor symmetry, as you can see, just to see if we can have a more flexible structure for our PDF, or if we need actually constraint for the US3 flavor symmetry. Here, in this image, you can see that with the addition of ESC pseudodata, we observe a dramatic reduction of the uncertainties of the proton G1P structure function, as you can see in this figure, where we are plotting with the yellow band the extraction with the current data available, and as you can see, there is a clear separation in the X region above X, above 10 to the minus 2, where we have actually existing data, and below 10 to the minus 2, where currently there are no existing data. So the uncertainties basically just explode, not being constrained by any data. But however, the inclusion of the ESC for the 3 different scenarios that I was talking about, the mid, low, and high G1, we see that now in the green, blue, and red band, we have a comparable uncertainties with the currently constrained X region. So we actually observe an incredible, incredible impact with the ESC data. Here instead, we repeated the same analysis, basically, with the inclusion of the deuterium data, so with the study also of the G1N structure function for the neutron. And in this, looking at these two images for the SU3 and without SU3, we can see that the inclusion of the deuterium pseudodata, we have a reduction by a factor 2 or 4 on the uncertainties compared with just the proton data. This reduction comes mostly from the constraint that deuterium or iridium data gives on the delta D distribution. Here, to assess the impact of the ESC pseudodata on the spin carried by quarks and gluons, it's also useful to consider the truncated moment of the quark singlet and of the gluon. And in this plot, we are showing the ratio of the uncertainties before and after ESC. To be clear, the more to the left, the better constrained is our uncertainties after the inclusion of the ESC pseudodata. For delta sigma truncated in the proton case, so the top left panel, we can see that the impact of the proton ALL depends significantly on the SU3 constraint. This can be explained as a weaker constraint on delta D plus and delta strange plus. And we pass from a no seizable constraint here without SU3 to an impact of 80%, a reduction of 80% or less with the inclusion of SU3. We also look at the case where the positive strangeness is removed with the green band, and we can see that it doesn't change much in this case. Delta G instead is much less sensitive to this imposition of SU3 or not. In the lower panel, you can see after the inclusion of pseudodata from deuterium and here of helium-3, we see a clear dependence on the theory assumption for the delta sigma truncated, going from no seizable impact without imposing of SU3. Okay. Instead, in the case of delta G truncated, we see that the impact at delta G gets less improvement with the inclusion of deuterium and helium, as gluon contributes only to the higher order of G1 of the nucleon. Also, SU3 doesn't really improve much on delta G, as it is not really sensitive to the gluon contribution. In general, we see that the total impact for this is around 69%. For APV, here instead, in the truncated moment on the right, we see a strong impact on the quark singlet, around 69% reduction, and it's not really dependent on the SU3 theory assumption, as G1 gamma Z is the dominant contribution to APV and wakes all the flavor, so all the flavor in the SU3 symmetry, they are weighted equally. Okay. The significant constraint in this region is explained as the strange elicited distribution as weight constraint from existing data, current data, I mean. So the future improved APV pseudodata are able to provide a much bigger constraint. And as last stuff, you can see on the left panel instead the different flavor of the PDF, of the ratio of uncertainties of the PDF extracted before and after the ESC pseudodata, and we have a good constraint for the red and blue curve in the strange sector and in the combination of the valence sector for the antiquark. To conclude, we have performed a dedicated impact study of future AC data on unpolarized cross-section and polarization asymmetries based on a global fit with the Monte Carlo approach. And there is a significant impact on the polarized PDFs, mostly in the valence case. The study of polarized asymmetries can greatly improve the determination of the elicited PDF, mostly at low X. And the interesting thing is also that ALL and APV acts in an almost complementary way on the quark singlet and the gluon moment, truncated moment. In general, the AC facility will provide unprecedented access to the flavor and spin structure of the nucleon in previously unexplored region of kinematics at a low X value. And we will wait for these real data to actually So thank you. And
thank you very much. I really appreciated this overview about what EIC will do for collinear PDFs, and particularly linking it then also to the spin structure of the nucleon, which is one of the main topics of the EIC.
definitely, definitely.
We are right now -2 minutes, including also the questions time. So unless there are some urgent questions, I would jump to the next talk. I don't see any urgent questions, but your talk was also very clear and
yes.
and really a great overview. So thank you very much.
Yeah,
and
it was also discussed a lot in the yellow report, so I probably there was a lot of discussion already. So thank you.
And let's go to the last presentation of today. That is Abdullah Farhat, who will talk about the application of deep neural networks to the reconstruction of DIS kinematics. That is aiming for EIC, but also for other future DIS facilities. I also will give you a 5-minute warning, Abdullah.
Thank you, Marcus. Hello, everybody. I'm a PhD student in the Department of Mathematics at Old Dominion University. And here I'm going to describe the work to use deep neural networks to reconstruct DIS kinematics. And so I'll begin by talking about the case that we're interested in, and particular DIS, of course, the lepton-nucleon collisions. These give us insight into the structure of the nucleons, and the reconstruction of the collision kinematics is a key component for the interpretation of the experimental results. These collision kinematics are reconstructed based on measurements of the scattering lepton, a hadronic final state, and knowledge of the beam energies. However, these measurements over-constrain the reconstruction of the event kinematics. With this in mind, there are multiple classical methods aimed to reconstruct the kinematics based on partial information from the measurements of the collision event. Due to this fact, they are subject to limitations related to bias due to QED radiation, the need for very precise measurements of the hadronic final state, the measurement of the kinematics of the scattered lepton, and finally, there's uneven performance of the classical reconstruction methods across the desired kinematic region. In an analysis, ultimately, there's some choice of the reconstruction method, and this choice can determine the size of the systematic uncertainty. A goal here is to automate this process to avoid having to make this choice and reconstruct the event kinematics in some ideal way. In particular, here we concentrate on a neutral current DIS where there's an electron in the final state. And the particular kinematic observables that we reconstruct are Q squared and X. So like I mentioned, these classical reconstruction methods are over-constrained by the measurements. And typically, the classical reconstruction methods use as inputs or independent variables these convenient variables, the energy and the polar angle of the scattered lepton, and the energy from the hadronic system in terms of delta, an energy longitudinal momentum balance, and the transverse momentum of the hadronic system. Also, we can characterize the hadronic energy flow by this angle gamma. Now, any subset of two of these variables can effectively reconstruct X and Q squared. There are three particular classical methods that we consider as comparison to our deep neural network model, and those are the electron method, the Jacques-Blondel method, and the double angle method. The electron method, as the name suggests, uses information from the electron. Some good characteristics is that it's precise, yet because it uses only information from the electron, it is sensitive to QED radiation. The Jacques-Blondel method, on the other hand, uses information from the hadronic system. So it is resistant to QED radiation, but needs precise jet energy measurements. The double angle method uses these two angles. There's not a need for precise jet energy measurements, but there's poor resolution at low x and low q squared. So the goal of our study is to reconstruct the kinematics of the DIS events by combining these multiple classical methods and utilizing complete information from the collision event. Our DNN approach was developed specifically and customized for this reconstruction problem. Now here's the model itself and how it is constructed. So we have two networks, one that will reconstruct q squared and one that will reconstruct x. And we build the models in the following way. Q squared, we reconstruct via three functions. A sub q squared is going to use a neural network to weight the classical, these three classical reconstruction methods. And then there are two additive correction terms where L sub q squared corrects the weighted average or the neural network weight via information from the lepton, and H sub q squared is an additive corrective term that corrects this this weighting via information from the hadronic system. Now, we further reconstruct X by in an almost identical way. However, we also use Q squared from the neural network as an input into the additive corrective terms. So every single one of these functions are going to be estimated by a neural network. And a specific architecture of a neural network that we developed for this purpose. Now, in general, a neural network is the sequential application of some affine transformations followed by a fixed nonlinear function. So in particular here, let's call capital psi just the set of all possible neural networks with d hidden layers that map from one space to another with a specific activation function, which is that fixed nonlinear function. Then ultimately, we can define a neural network in the following way. We start off with our input, we call it x here, and then we sequentially apply some affine transformation, capital A sub I, and then we apply a fixed nonlinear transformation. And we do this repeatedly up until our desired depth of the network, at which point we have the output of the network. Now, instead of searching for the best network to perform the reconstruction in that class of neural networks, instead we consider this new set. I call it capital phi, which essentially will follow the process of the neural network through the sequential application of affine transformations followed by some fixed nonlinearity. But then at the end, as opposed to taking the output of the last layer, it sums up and weights the outputs from every single hidden layer. Now there's reasons for using this this subclass of neural networks. Now, first of all, in terms of the approximation capability of neural networks, in general, they have universal approximation capabilities, which implies that they can approximate any continuous function to arbitrary accuracy. I showed that this subclass also has the same universal approximation capability. The next thing that's I show is that by increasing the depth of the network, i.e. the number of terms in the sum, the error will necessarily decrease. And finally, there's some computational efficiency in terms of using the summation of the values from each of the hidden layers, which avoids a problem called vanishing gradients, which arises in the backpropagation algorithm. And ultimately, the task here is to select the optimal neural network from our class of functions, which entails finding the collection of parameters that defines the affine transformations that will minimize the generalization error. So with a randomly selected data set, if the size of the data set is sufficiently large, this generalization error can be approximated by an empirical error, which is the average of some loss function, which measures the discrepancy between the observed output in the data set and the output of the neural network. Now, the loss function that we use in particular is this logarithmic mean square error. The reason that we use the logarithmic mean square error as opposed to the ordinary mean square error is due to the fact that the variables q squared and x have a large range spanning over multiple orders of magnitude. And in order to avoid the multiple scale, we take the logarithm. One final note in terms of the training of the networks and determining our optimal network. Due to the universality of the networks, there is, in theory, a model that can achieve zero empirical error. But this is not necessarily ideal, especially in the presence of noise in our data set. The model will overfit to the data and lose its generalizability. So we add a L1 regularization term that provides sparse optimal solutions. And by sparse, I mean there's a minimal number of non-zero parameters that define the network.
You have 5 more minutes, Abdullah.
Thank you. So the final optimization problem is here. We minimize the average of the loss function plus this term lambda, the regularization parameter that determines the extent of the sparsity that we want to induce. And we solve this using stochastic gradient methods with small batch sizes. The specific data set that we use is simulated data sets from the Zeus experiment, and we reconstruct q squared and x based on these sets of variables. We use the Zeus experiment because there's dedicated simulations and the reconstruction methods are well studied. So the selection of the events that we choose mimics, the process of the selection mimics very similar to the selection processes used in previous Zeus analyses for this NCDIS process. When we train the models, we use the entire phase space, but ultimately we compare the neural network to the classical reconstruction methods on specific bins in the kinetic space. And here's the distribution of our data set on the left. And we have 8 bins over which we compare the neural network to the classical reconstruction methods. Now here's some of our results. Across each of the 8 bins, here's the distribution of log q squared minus reconstructed minus log q squared true. You can immediately see, just based on where the mean is and the standard deviation of these plots, that there's some improvement in comparison to the neural network with the classical reconstruction methods for q squared here. Similarly, we can see that for x. And so this is one diagnostic measure. The second diagnostic measure that we use here is the resolution. What we're looking for here is a smaller resolution, and you can see that across our comparative bins here, the neural network is superior. And some main reasons for this, so some main things that we see is that there's more precise estimation in the lower bins, and in the higher bins, the estimation is better because of the rejection of outliers. So while we train the models with events dominated in lower q squared and x, it did not prevent the neural network to have a reasonable performance on other regions of the kinematic space. And the nice thing about this neural network is that by incorporating all of this information, we can have a definition for q squared and x that is reasonable for many comparisons to the theory. And here's some just a final notes on outlook and conclusions. With the appropriate selection of a training set, that we can see that the deep neural network models can outperform the classical reconstruction methods. We are concluding a study on the impact of the improved determination of the kinematics on the determination of average values on the event shapes. And the next step of this project is to extend the results to semi-inclusive and exclusive processes. And something to look out for is there's a paper under internal review that we are in the process of completing. Thank you.
Thank you very much, Abdullah, for presenting your machine learning study on reconstruction of DIS kinematics. Are there questions for Abdullah? I don't see any question. We are more or less on time. So just let me ask you one high-level question. You were coming from applied math and jumped on a DIS, so high energy nuclear physics problem. Just when looking at the interplay of these two fields, where do you think we can learn from each other? That is very important because we already have discussed a couple of times in this discussion here about AI joining experimental methods. And we saw AI being used for, or machine learning being used for theoretical calculations. And we are looking here to the future. So would you like to make a few comments on that?
Sure. I think that there's a lot of opportunity for improvements to both fields in the applied math side and on the nuclear physics side. And I think that it requires some understanding of what the problems are that are being faced with data sets in the physics community. And the determination of these problems and sharing them with mathematicians can improve the types of models and methods that we try to build. And similarly, the ways that we solve problems and the line of thinking in terms of this machine learning can have some impact on the way that the nuclear physics community sees and interprets their own data sets. And as we've previously discussed, I think that there should be some access to these problems and some data sets that would allow mathematicians to experiment with the problems in the community.
Thank you very much. Thank you for the presentation and all to the other presenters. Thanks everyone for attending and for the questions which we had. This now concludes the second morning session in future experiments and facilities, and we will continue at 12:15 p.m. Eastern Time, 6:15 p.m. Central European Time with the last session in the future experiments and future facilities session. Thank you very much.